automating the code around a large language model, the harness, it can actually boost its benchmark performance by up to 6 times.
Yeah.
But there is a catch that's currently just bankrupting ML teams on compute costs.
Right.
To figure out if a newly generated harness is actually an improvement, current frameworks force you to evaluate it against this massive static test suite at every single iteration of the search process.
Yeah.
And it is computationally ruinous.
Utterly ruinous, yeah.
So today, welcome to AI Paperslop, where we're doing a deep dive into the source material for a solution to this. The paper is titled Task-CoEvolve: Efficient Harness Optimization via Adaptive Validation Task Selection.
It's a great paper.
Yeah, it's from researchers at Tsuyuki Miyai, Kiyoharu Aizawa, and Toshihiko Yamasaki at the University of Tokyo.
Right.
And their system, Task-CoEvolve, it solves this compute bottleneck by actually co-evolving the validation tasks alongside the harness itself.
Exactly.
So by tracking historical variance, it samples only a small shifting subset of tasks that are actively challenging the model on that specific iteration.
Then it uses some very clever mathematical estimators to calculate what the full set score would have been.
Yeah.
And the results are striking. On complex long horizon benchmarks like Terminal Bench 2.1, it cuts evaluation tokens and wall clock time by up to 80% while still matching full search performance.
Which is huge.
Yeah. And on text classification, it actually beats full set evaluation by preventing the meta agent from overfitting to the validation set.
Right, because we are looking at a fundamental shift here in how agentic systems are evaluated and, well, how they're improved.
Yeah.
Historically, the focus has been entirely on optimizing the harness, right?
Yeah.
Like the prompt logic, the retrieval pipelines, the tool use scaffolding.
The actual code surrounding the model.
Exactly. But this paper proves that optimizing the actual curriculum used to evaluate that evolving harness is just as critical.
I mean, for teams that are hitting severe API limits or burning days of compute on these evaluation loops just to squeeze out a few percentage points of accuracy, addressing this evaluation bottleneck is just, it's non-negotiable.
I really want to look closely at that bottleneck because the current state-of-the-art methodology, it feels incredibly inefficient when you visualize what's actually happening under the hood.
Oh, yeah.
It's like, okay, imagine taking a student who is learning calculus
Okay.
and giving them a 100-question math test to gauge their progress every single day.
Right.
But if 40 of those questions are just basic addition,
Yeah.
and another 40 are unsolved string theory equations, that student is wasting 80% of their time on that test.
Totally.
The addition is trivially easy, the string theory is impossibly hard, and crucially, neither of those extremes tells the teacher how good the student actually is at calculus.
Right. The only actual signal is in those 20 middle-tier calculus questions.
Exactly.
And the current frameworks, things like meta-harness, they operate exactly like that inefficient test. You have a meta agent acting as the developer. It looks at the execution logs from the previous evaluations, identifies where the current harness failed, and then it generates new candidate code to fix those issues.
Right, standard optimization loop.
Right. But to validate if that new candidate code is actually superior, the system runs it against the entire validation set.
Every time.
Every single time. And the paper reveals that over 70% of the evaluation budget in these runs is completely wasted on tasks that fall into those extremes you mentioned.
Wow, over 70%.
Over 70%. The meta agent is just paying for inference on tasks that every single candidate harness can already solve perfectly, or on tasks that are so far beyond the base model's capabilities that no little harness tweak is going to solve them.
Which means teams are literally just burning millions of inference tokens to confirm data points they already have high confidence in.
Exactly. And the severity of that waste, it scales with the complexity of the benchmark.
Right.
Like in something straightforward like online text classification, throwing away 70% of your tokens is, a financial annoyance.
Sure.
But the real problem surfaces in long horizon tasks. So if you look at Terminal Bench 2.1,
Yeah, let's talk about that.
we're talking about LLM agents that are sandboxed in terminal environments. They're executing bash commands, reading massive error logs, compiling code bases, and they're running scripts for tens of minutes at a time.
Right, so the context windows are just filling up rapidly.
Exactly. When you force a static evaluation strategy in those environments, evaluation stops being just a step in the process and it becomes the central, crippling bottleneck of the entire optimization loop.
Okay, so if the solution is dynamically picking tasks, the immediate red flag for me here is how the system defines what a quote-unquote calculus-level task even is.
Right.
Because the capability frontier of the model, isn't static, right?
No, not at all.
If the meta agent is doing its job and actually improving the harness, what is incredibly hard on iteration 1 should theoretically become trivial by iteration 10.
Yes.
So the curriculum has to adapt.
Curriculum absolutely has to adapt. And they handle this using the Bernoulli variance of past outcomes.
Okay, unpack that. Bernoulli variance.
So instead of looking at the static difficulty of a task, they look at the historical success rate of that specific task across the previous iterations of candidate harnesses.
Right.
The variance peaks when success and failure are perfectly balanced, meaning the candidate harnesses are disagreeing on the outcome.
Ah, I see.
Right. If half the candidates solve a task and half fail, that task is highly informative. It's sitting directly on the edge of the model's current capability frontier.
Right.
So the system weights it heavily for sampling.
So a task with a 100% success rate or a 0% success rate, it just naturally filters itself out because the variance drops to 0.
Exactly.
But wait, if a task has a 0% success rate early on and its variance drops to 0, doesn't it just get ignored forever?
Yeah.
Like, what if the meta agent writes a brilliant piece of code in iteration 15 that suddenly unlocks that whole category of task?
Right. And you're touching on the exact reason they had to introduce mathematical safeguards into the sampling logic.
Okay.
They apply what is called a floor weight to the tasks.
Floor weight.
Yeah. So even if a task has 0 successes and technically 0 variance, it's never banished completely. It maintains this small baseline probability of being sampled.
Just in case.
Just in case, yeah. And they also introduce an uncertainty bonus, which operates similarly to upper confidence-bound algorithms used in reinforcement learning.
Okay.
It prioritizes tasks that just have fewer total observations.
Ah.
This ensures the system doesn't confidently ignore a task based on just 1 or 2 early failures before the harness had a real chance to evolve.
So it's actively balancing exploring neglected tasks with, exploiting the high variance tasks it already knows are informative.
Exactly.
And I assume they have the data to prove this shifting frontier actually exists in practice.
They do, yeah. And the Terminal Bench 2.1 runs illustrate it perfectly.
Oh.
So at iteration 0, there were 32 tasks in the pool that no candidate harness could solve. It was just a brick wall.
Right.
But by iteration 10, as the meta agent evolved the scaffolding, that number dropped down to 21.
Wow.
Yeah, 11 previously impossible tasks suddenly became solvable.
That's amazing.
And because Task-CoEvolve is tracking variance dynamically, the sampling distribution naturally chased that shifting frontier.
It followed the progress.
Right. It abandoned tasks as they became too easy and reallocated that evaluation budget to the new edge of the model's capabilities.
Okay, that makes intuitive sense for the sampling side, but the scoring side seems completely compromised to me.
How so?
Well, if Harness A gets evaluated on a subset of these really hard, high-variance tasks, and Harness B gets evaluated on a subset of slightly easier tasks that just, happen to be sampled,
Right.
Harness A is going to score lower. It will look objectively worse on paper, even if the underlying code is actually superior. You can't just compare raw scores from 2 completely different exams.
Yeah, you're right. And that is the core statistical challenge of the paper. You cannot use the raw score of the subset.
Right.
So instead, they use Horvitz-Thompson estimation to mathematically estimate what the full set performance would have been.
Okay. Horvitz-Thompson estimation.
Yeah, they weight the results based on each task's inclusion probability. But because datasets behave differently, they actually rely on 2 different statistical estimators guided by the initial baseline runs before the search even begins.
Let me guess, it depends on how the success rates are distributed across the dataset.
Yes, exactly.
Okay.
So for their text classification benchmarks, the success rates tend to cluster heavily near the extremes, 0 or 1.
Right.
For that distribution, they use Hajek estimation.
Hajek.
Yeah. The logic is that if a rarely sampled task happens to be drawn, its outcome is likely going to be very close to the pool's mean anyway.
Okay.
Weighting the outcome directly works well in environments where performance is largely binary and predictable across candidates.
But Terminal Bench 2.1 wouldn't look like that. Because if the tasks are highly complex, the mean success rate is going to sit closer to the middle, probably around 50%, right?
And that is exactly where the Hajek estimator breaks down.
Ah.
Right? If you randomly sample a task in Terminal Bench that is almost always solved, but it had a tiny probability of being included in that specific subset, weighting its raw outcome based on that tiny probability can wildly distort the total estimated score.
Right, because one lucky draw on an easy task could make a terrible harness look like it's state-of-the-art.
Exactly. So to solve this, for environments with spread out success rates, they switched to an anchored difference estimation.
Anchored difference, I'm trying to visualize the math on that. If it's anchored, it must be measuring the deviation from an expected baseline rather than just the raw success or failure.
That is the precise mechanism, yeah. They weight the deviation from the historical success rate of that task.
Okay, give me an example.
So let's say a task is usually solved, so its historical anchor is a 1. If the new harness solves it, the difference is 0. You weight that 0, and it doesn't distort the estimated score at all. It just confirms what you expected.
Makes sense.
But if the new harness fails on that typically easy task, the deviation is negative.
Ah.
And that negative deviation gets weighted heavily by the low inclusion probability, signaling to the system that this new harness caused a major unexpected regression.
Oh, wow.
Yeah, because the anchor cancels out an expectation. They can compare scores from wildly different subsets on a level playing field.
That is a brilliant way to isolate the actual signal.
It really is.
So let's look at what happens when they run this mathematically leveled playing field in practice.
Yeah.
Because the first set of empirical data is on the online text classification benchmarks.
Right.
They're running law bench for legal texts, symptom to disease for medical texts, and USPTO 50K for chemistry.
Mm-hmm.
And looking at the results, there's a finding that completely defies common sense to me. At a 20% evaluation budget, Task-CoEvolve doesn't just match the performance of the full 100% search method, it outright beats it.
It is easily the most counterintuitive finding in the whole paper.
Yeah.
So they used Quad Opus 4.6 as the meta agent, and it was tasked with writing harnesses for a GPT OSS 120B classifier model.
Okay.
The baseline few-shot accuracy across those datasets was 41.6%.
Right.
But when they deployed Task-CoEvolve with just a 7% evaluation budget?
Meaning the meta agent only saw 7% of the validation tasks per iteration.
Exactly. At just 7%, accuracy jumped to 47.6%.
Wait, so they improved the accuracy by 6 full percentage points using 16 times fewer samples than a full search.
Yeah.
I imagine if they gave it slightly more breathing room, say a 20% budget, the gap just widens.
It does. So at a 20% budget, Task-CoEvolve hit 49.3% accuracy on the held-out test set.
Wow.
And the full search method, which evaluates every single task, every single time, burning maximum compute, it only hit 48.6%.
Okay, how is that mathematically possible? Looking at less data should inherently give the meta agent a lower resolution picture of the model's performance, right?
Do you think so? Yeah.
How does a lower resolution picture lead to a better final product?
It comes down to regularization and the risk of overfitting.
Overfitting, okay.
Right. The full search method evaluates the exact same static validation set every single iteration.
Right.
So over time, the meta agent starts overfitting to the specific quirks of those validation examples. It writes highly specialized harness code that perfectly solves the validation set, but then it fails to generalize to the held-out test set.
I see.
And Task-CoEvolve prevents this by constantly shifting the evaluation samples based on variance. It forces the harness to prove itself on a dynamically changing subset of difficult tasks.
So the meta agent can't memorize the test because the test is always moving.
Exactly. That constant rotation acts as a regularizer, forcing the generation of far more robust and generalizable code.
It's basically the difference between memorizing the answers to a specific practice test versus actually learning the underlying concepts, because the practice test keeps targeting your blind spots.
Perfect analogy, yeah.
It makes total sense when you frame it as a regularizer. But let's move from text classification to the real heavy lifting.
Yeah, let's do it.
Because for the ML engineers listening who are trying to optimize massive agentic workflows, I mean, the text results are nice, but the cost savings in long horizon environments are the main event here.
Oh, absolutely.
Let's unpack the Terminal Bench 2.1 results.
So Terminal Bench 2.1 is where the financial and temporal arguments for this paper just become undeniable.
Yeah.
They tested the framework using GPT 5.6 Luna and Quen 3.635B A3B as the base models.
Okay.
And with a 20% evaluation budget, Task-CoEvolve matched the full search performance with almost zero degradation. It was about 1% lower on the final metric, which literally translates to missing one single task out of the 89 in the benchmark pool.
I mean, giving up one task is a rounding error. What was the compute reduction to achieve that?
For GPT 5.6 Luna, the total input tokens for the full search baseline were roughly 2.9 billion.
2.9 billion tokens.
Right, there is an enormous amount of context being processed just to evaluate harness candidates.
Yeah.
But Task-CoEvolve plummeted that down to 579 million tokens.
Wow.
That is an 80% reduction in token costs.
That is incredible.
And the wall clock time was halved, dropping from 22.2 hours of search time down to 11.5 hours.
Cutting the compute budget by 80% and saving 10 hours of active search time for a 1% trade-off? I mean, that's an absolute no-brainer for any production pipeline.
Without a doubt.
But I do want to flag a nuance from the ablation studies that caught my eye.
Oh, the random baseline.
Yeah, they tested a baseline called random resample, where instead of variance-weighted selection, they just picked 20% of the tasks completely at random every iteration.
Right.
And that random method actually saved even more tokens, like a 96% reduction.
It did.
But the final harness performance was terrible.
It performed 3.3 points worse than Task-CoEvolve, which is a significant drop in these agentic benchmarks.
Right.
And the massive token disparity explains exactly why it failed. If you randomly sample tasks in a complex terminal environment, you're inevitably going to spend your limited budget on the fast, easy tasks.
Right, because there are more of them.
What, just statistically? Yeah, and these are the tasks that terminate in a few seconds. They run a basic command, and they consume very few tokens.
Ah, I see.
But Task-CoEvolve, by hunting for variance, it intentionally seeks out the long, multi-turn, highly complex tasks.
So it's actively looking for the tasks that generate massive error logs, require real debugging, and just eat up context.
Precisely. Those high-variance tasks consume more tokens, but they are the only tasks that actually differentiate a capable harness from a weak one.
Right.
Task-CoEvolve used 3.2 million tokens per trial on average, compared to random resample's 0.7 million.
Okay.
So it's spending its budget exactly where the signal is highest, rather than just optimizing for the absolute lowest token count, regardless of utility.
That makes a lot of sense. So we've talked a lot about the math of how it picks the tests, but I'm still trying to visualize what this meta agent is actually writing when it optimizes a harness.
Right, the actual code.
Yeah, it's one thing to say harness optimization, but I want to get inside the black box and look at the tangible, clever modifications this AI discovered.
Sure.
Let's start with the text classification benchmarks. What did it actually code?
So the qualitative analysis of the generated code is fascinating because it highlights how rigid human-designed harnesses can be.
Okay.
For the text classification, the meta agent realized that different datasets require fundamentally different ways of retrieving information.
Right.
Like legal texts in LawBench rely on specific phrasing or word combinations. But chemical molecules in USPTO50K, they rely on character substrings.
Which means a single tokenizer is always going to be a compromise. You can't optimally parse legal jargon and chemical compounds with the exact same logic.
Exactly. So the meta agent solved this by writing a harness that uses two tokenizers simultaneously.
Two.
Yeah, it builds one index based on word burgrams and a secondary index based on character n-grams.
Wow.
Then it ranks the stored examples separately under each tokenizer and merges those two rankings using a reciprocal rank fusion algorithm.
That's so clever.
It is. And beyond that, it wrote custom logic to dynamically penalize duplicate labels when filling the prompt.
Why?
This ensured the LLM always saw a highly diverse set of examples in its context window. It basically built a dynamically adapting retrieval augmented generation pipeline from scratch without knowing beforehand which specific data set the query was coming from.
That is incredible. And what about the long horizon tasks? Like, what did it write for Terminal Bench?
Oh, in Terminal Bench 2.1, the meta agent found a fatal flaw in how the stock agent managed time.
Time. Okay.
Yeah, so the benchmark has strict time limits. And the stock human design agent always slept for a fixed predetermined amount of time after typing commands, just to let the system process.
Like a static wait command.
Right. And if the agent compiles a massive code base, it might actually need to wait. But if it just runs a simple else command to list directory contents, waiting for a fixed duration just burns precious seconds.
Right.
And the meta agent identified this massive inefficiency in the execution logs.
So it wrote a custom script to bypass the fixed sleep.
It evolved a harness that executed an active polling script.
A polling script.
Yeah. So instead of sleeping, the script continuously checks the terminal state. It's looking for the shell prompt to return. Specifically, it scans for a hashtag or a $sign at the end of the line, indicating the terminal is quiet and ready for input.
Oh, wow.
And the exact millisecond that prompt returns, it cuts the wait short and immediately executes the next action.
That's brilliant.
Yeah, by shaving off those wasted seconds across hundreds of commands, it saved massive amounts of the overall time budget, preventing timeouts and allowing the agent to complete far more complex tasks before the environment shut down.
Oh, I get it. It's like impatiently spamming the refresh button on a loading screen instead of just staring at it for a fixed 10 seconds.
Yes.
It's exactly what a human sysadmin does. You don't stare at the screen, you just wait for the prompt to return.
Exactly.
But as clever as that is, there has to be a ceiling to this optimization, right?
Oh, absolutely.
Because the scaffolding can only do so much if the underlying model is fundamentally flawed.
There is absolutely a ceiling, and the paper actually explores this through an ablation study using DeepSeek V4 Flynn.
Yeah, let's hear it.
And this is a crucial point regarding the limits of automated harness engineering. DeepSeek V4 is an incredibly capable model right out of the box.
Right.
Using just the baseline unoptimized harness, it scored 70.8% on Terminal Bench 2.1.
Okay.
When the researchers let the meta agent try to optimize the harness around it, it couldn't find a single improvement.
Really? Not even one?
Not one. After the full search, the best candidate harness still scored exactly 70.8%.
Oh, wow. So if the base model's reasoning capabilities are already saturated for that specific benchmark, no amount of clever polling scripts or dual tokenizers is going to squeeze out more performance.
Right.
The scaffolding only helps if the model actually needs to be scaffolded.
That is the big takeaway here. Task-CoEvolve makes exploring the design space vastly more efficient. It finds the optimal harness 80% cheaper and twice as fast.
Yeah.
But it cannot create performance headroom that simply doesn't exist in the underlying model. It optimizes the extraction of capability, but it doesn't create new capability.
Man, this entire framework raises such an incredible implication for the future of AI development.
It really does.
We are already looking at systems where meta agents are dynamically rewriting their own operating code to improve performance. But what Task-CoEvolve introduces is the AI selectively curating the very curriculum it is evaluated against.
Yes.
It's deciding mathematically which tasks are informative, and it's just ignoring the rest of the human-designed benchmark.
And that leads to a really profound question about evaluation as a whole.
Yeah.
If AI is now determining how it should be tested to guide its own evolution, relying on standard static human benchmarks seems increasingly fragile.
It does.
The next logical step isn't just the AI selecting from a pool of human-designed tasks. The next step is the AI generating the tasks themselves, perfectly calibrated to its own shifting capability frontier.
Wow. If the AI is writing its own code, generating its own test questions to probe its weaknesses, and then mathematically grading its own test, we are rapidly approaching a closed-loop, self-improving ecosystem.
We really are.
The question for ML engineers isn't just how to optimize the search anymore. It's where the human evaluator even fits into the loop once the benchmarks themselves become obsolete.